Hey everyone, so I just wanted to pick up where we left off looking at a simple linear regression the other day and talk about doing a multiple linear regression. So technically how we do a multiple linear regression is very simple. We can actually just add more variables to our regression and get some information about the coefficients and the R-squared value and all of that stuff. But I want to use this as an example, and I'm going to use our existing educational data set as an example of kind of what we want to be looking out for, especially when we start to throw multiple variables into a model. So I'm beginning with the sample file that I had uploaded after class yesterday, and I want to just take a minute to look at some of the other variables in our file and kind of how they behave, and then explore how what we find there might affect what type of multiple linear regression we would do. So the first thing you'll probably remember is that in our work here, we started out by looking at histograms of meals and academic performance. And so I'm just going to go ahead and quickly run this. I'm going to get to the file here. And so I'm just going to say, whoops, where did I put this? Hang on. Sorry about that. So let's just do this. I know you can't see what I'm doing right now. I am going to run this file. Okay. Right, and so, ooh, that's a whole lot of stuff happening on a single plot. Not what I intended. But you may remember, let me actually just get rid of this plot for a second here. Right, I'm just going to, again, if you remember what we did with our print statements, let's see if this is a little bit more useful. Right, so still got some weirdness going on. But here are, this is my meals percentage here. This is the histogram of my academic performance. And the question that we want to answer with this, right? So we did our scatter plot prediction. So I'm going to get rid of my histograms for a second here. Just to remind you all of what we were doing. We were looking at the relationship between the percent of students on free and reduced lunch and comparing that to academic performance and printing out some related coefficients, intercept, et cetera, and then highlighting schools that are outperforming our expectations, right? So we've actually printed out those schools here, and if I have not messed this up, right, so we have, here's a relationship that we're seeing between percent of students on reduced lunch and academic performance, slight negative relationship. Here are outperforming schools, and maybe we want to investigate what's going on at their schools, the schools that's making them succeed despite their relatively high percentage of students on free and reduced lunch. Okay, so that's one way that we can approach this. Now, one of the things that we want to look for, right, and this came up in class, is, well, how do we know how significant this relationship is? How important is it, right? So we know that in the story that we read, it was just kind of taken, I think, a little bit as received wisdom that, you know, it could be harder to, the performance on standardized tests is probably going to be less for students with a coming from a lower socioeconomic background, if they're English language learners, if they've just moved to the area, et cetera, et cetera. And so that was kind of received wisdom a little bit. And so the thing that I want to look at here is, if we look in slightly more detail at our data set, what other relationships do we find? We may or may not find them interesting, but also when we start throwing multiple variables into our regression, what are the things we need to watch out for, right? So we're actually going to come across sort of a variation on Simpson's paradox, and I want to show you how that manifests when we look at multiple linear regression. So let's get rid of this guy. And sorry, so I'm going to go ahead and get rid of these histograms, and instead I want to look at, so instead of looking at the histogram of this, I want to look at the relationship between, I'm going to look at some different parameters, right? So one of the things that I'm interested in is school segregation, right? And this is actually in our data set as the percentage of students that are white. So what I'm curious about is if you're in a highly segregated school, does that correlate with performance? Yeah, basically, is segregation kind of a contributing factor to performance, right? There's reasons why we might think that is the case. And the question is, to what extent is that the case? And is there maybe something else going on that we should be aware of? So in this case, I'm going to go ahead and plot. I'm going to get rid of this stuff because I am not so interested in these. Right, I'm just going to go ahead and, just focus on this scatter for a minute, okay? So I have the percentage of students that are white, I have academic performance. Let's go back here and see what we get. Oops, left a histogram in there. Sorry, folks. Right, if you don't actually specify separate ones, it's going to plot them on the same. Okay, so what I'm seeing here is what looks like a moderate positive relationship between the percentage of white students in a school and the academic performance. So I want to get a little bit more detailed on this. So I am going to use something from a library called statsmodels, and I'm going to use that, and it's going to print out a whole host of a whole table of values that's going to let us get a little bit more detailed about what is going on here. So first, the thing I'm going to do is I'm going to import statsmodels. It's an API. API as SM. Okay, and the next thing I'm going to do, and I realize this is getting a little confusing to look at here, so I am going to get rid of these histograms. I don't have to look at them anymore. And I'm going to come down here. Here's sort of my original linear regression. This is my scikit-learn linear regression, and I'm going to create big X. I'm going to call this stats, just so we can tell the difference between them. And I'm doing basically the same thing as I am up above, but again, what stats models is going to print out for me. So I can actually just do this. What it's going to print out for me is a little bit different. So I'm just going to call this y stats. And then I'm going to add a constant to this. So this is going to not force my y-intercept to go through 0, which is probably going to give us a better fit on our line. And I can just say add constant, and I'm just going to give it x stats. Okay. Now, what is the next step? I'm going to say, okay, I'm going to create the model. Okay. And so my model is going to be ordinary least squares, which is actually, I'm pretty certain what scikit-learn is using as well. Sorry, I realize I'm like way down at the bottom here. What scikit-learn is using as well, but it just doesn't happen to say it. And so I'm going to just say, I want you to fit the model. My predictions are going to be whatever I predict with the model, right? Again, this is just sort of straightforward. And then I want to print the model the model summary, okay? And so this is going to give me a nice table of values that I can then interpret. So I'm going to go ahead and turn off my plot showing here so that I can just focus on my table of values. Oops, and we've got problems here. Okay. Oh, sorry, model predict. Typo. Okay, so what are we seeing here? We are seeing that there is a 1.4 correlation coefficient between the percentage of white students and academic performance. We look at our R squared. Our interpretation of this is that this is describing 13% of the variance in our data, which is not high. So, yeah, we've got something going on here, but it's not really telling us much about our data. We could, again, just kind of futz around with this and say, okay, let's go back to meals, which we had looked at yesterday. Let's go back to meals and see what we get when we do that. And in this case, what we're seeing is meals is describing maybe 27% of this, or 28%. Again, that was a negative relationship. That's at 1.8, which is what we also saw in class. Not that large a contributing factor. So if we look at some of the other data values that we have available, we also have one on average education. And I think a couple of you were looking at this in class already. And so average education is sort of a numerical value that encompasses whether your parents graduated from high school, college, graduate school, etc. Now, I'm going to make a quick fix here, which is to say that there are some missing values. There are some schools in our sample set that do not have values for average education. I have removed those. It is less than 1% of the data. So obviously I wouldn't want to do this if this was a third of the data or half the data, but it is a sufficiently small number that I don't feel bad just kind of eliminating them. So hopefully if I did that correctly, I'm now going to get something similar. Okay. So again, if we look at this, what do we see? Oops, I think we see that we have not actually changed anything. Sorry, it's this part. Okay, so now we're starting to get something interesting. We're describing 42% of the variance in our output is coming from the average education of students' parents. So that's a positive relationship, right? Our coefficient is pretty high. So a question that we might ask is, well, what if we look at average education and level of segregation? Both of those were positive, right? So what if we put those both together? What do we get? So the process for doing that is dead simple, right? All I have to do is literally add it in there. But I want you to pay very close attention to what happens to my outputs when I do this. Okay, R squared, not super different, right? I've got 4.37 versus 4.26. But notice that the coefficient for x1, which in this case is average education, is still pretty large. That's actually gotten larger and it's not more positive, right? It's gotten larger, it's still positive. But we've seen a flip in the sign in percent white, okay? This is what we would expect if we have some measure of quote unquote Simpson's paradox, or basically it means that there is a relationship between these two variables. They are correlated with one another, okay? And so when we see this sign flip in particular, this is an indicator that our independent variables, as we are suggesting, are not actually independent. So we need to kind of go back to the drawing board and say, which one of these do we think is relevant to include? Which one is going to help me explain the most variance of my potential model? Because if I include both of them, I'm going to get weird behavior because they are correlated with one another as well as with the outcome. So we're going to come back in a minute and I'm just going to show you what that correlation looks like in a plot. It's not a gorgeous plot, but it sort of illustrates the point here and why it's really important for us to look at all of our covariates together and also be really careful about what we choose to put in our multiple regression model and how we should kind of go stepwise through creating that multiple regression model to make sure that we're not putting in variables that are quote unquote independent variables that are actually correlated with one another.